Hello, and welcome to today's featured product introduction webinar brought to you by ROHM Semiconductor. Today we're going to introduce two new op-amps with zero drift, ultra-low offset voltage, and high accuracy. During today's presentation, we are going to start by discussing the sensing challenge and then move on to the big question, how do we achieve better sensing accuracy? That will lead us into talking about the advantages and design of zero drift op-amps. We'll walk through a current sense application example, discuss how these zero-drift op-amps can reduce your system design burdens, and finish with some applications. With that agenda in mind, let's go ahead and get started. The sensing applications today are increasing everywhere we look. Starting in the lower left, we look at consumer electronics. These can be devices in our homes or even wearables. With the rapid growth of the Internet of Things, just about everything has built-in sensors. More accurate and more power-efficient sensing can help improve performance and power efficiency of end products. Moving to the industrial space in the center, it is a similar story. Sensors are going into everything and everywhere as every process and equipment in modern factories need to be monitored. Not only is the number of sensors increasing, but the accuracy has to improve to get better performance. Finally, taking a look at the automotive market, we are again witnessing an explosion in sensing and control systems in automobiles and EVs, as well as hybrids and internal combustion engine vehicles. Safety, comfort, and convenience are the main drivers. There has been massive growth in sensing in pretty much any application we can think of. Op-amps are a fundamental building block in sensing systems. We will be discussing in detail today where and how they are used in example application. But first, let's back up a second and talk about the sensing challenge. Obviously, we start with the sensor. There are lots of different kinds of sensors, and what we're talking about here applies to almost any sensor. Most sensors have an analog output, but we eventually need to get that signal to a microcontroller where we can analyze and make decisions on the data. The MCU may transmit that information up to the cloud, provide feedback to the users, or provide control feedback to the system. To enable all of that intelligence, we need to get highly accurate sensor data to the MCU. The problem is that the signals coming out of these sensors are small. They could be easily corrupted by noise and might not be readable by the MCU or its ADC. We need something to boost that signal to get it to the MCU. Obviously, the way to do that is with an op-amp in an amplifier circuit. After amplification, the signal is large enough for A to D conversion to get digital data to enable those decisions and actions. At a conceptual level, this is very easy to understand. But in reality, it's a difficult challenge. So let's talk about some of the difficulties. One of the big challenges is the limitations of the op-amp. Ideally, that signal that we've amplified is now a large, clean, undistorted signal centered around the 0 point as the signal varies up and down. Unfortunately, op-amps are not perfect. Real op-amps have input offset voltage. Ideally, if the two inputs to an op-amp are at the same voltage, the output would be 0. With real op-amps, a small difference between the two inputs is required for the output to be 0. This differential voltage is input offset voltage and contributes to error at the output by a factor which is proportional to the op-amp's non-inverting gain. A secondary challenge is that the input offset voltage changes with temperature and aging. Temperature coefficient is called drift. Changes in the input offset can look like a real signal, and we don't want that. Amplifying these input offset voltage error factors along with the sensor signal can decrease the sensing accuracy. The key to high accuracy sensing is minimizing these error factors. That naturally leads to the question, how do we achieve high accuracy sensing? The simple answer is we want better op-amps. We need them to have ultra-low input offset voltage and minimal input offset drift with temperature. We want to minimize those error factors we just talked about on the previous slide. And so here today, I want to introduce you to two new products from ROHM Semiconductor, the LMR1002FLB and LMR1001YFC. These are zero-drift op-amps that deliver ultra-low offset voltage while also reducing the temperature-based offset voltage fluctuations to nearly zero. These are the better op-amps that we're looking for to solve our sensing challenge. What is the advantage of zero-drift op-amps? Here we have on the left a comparison chart of the offset voltage temperature drift for two op-amps, a standard op in blue and a ROHM zero-drift op-amp in red. As you can easily see, the input offset voltage in a standard op-amp changes dramatically over our temperature range of interest. It not only changes sign from negative to positive, but it isn't even a linear curve. It starts out near negative 20 microvolts, increases to above 30 microvolts, and then comes back down at the end. That means in your system, you will need to monitor the temperature of your environment and apply a complex correction to calibrate out this error. In the red, you see the new LMR 1002FLB zero-drift op-amp performance over the temperature range. It stays right around that zero mark with a typical offset drift of only 10 nanovolts per degree Celsius. That is more than a 10-time reduction in offset drift when compared to the standard op-amp. This chart provides some key specifications for three ROHM low offset voltage op-amps. We have the two new products that I've talked about and compare these to a standard low drift op-amp but not zero drift. Let's compare a few of these key specifications. The input offset voltage of the zero drift op-amps are 9 and 12 microvolts. These are an order of magnitude better than the standard low offset amplifier. And then you see the input offset voltage temperature drift for the 1002FLB. A maximum of only 50 nanovolts per degree Celsius. This is near zero across the temperature range. In the far right column, I want to highlight that the new LMR 1001YFC op-amp is AEC Q100 qualified for automotive applications. Finally, we see a few other key specifications at the bottom. These are all single-channel op-amps that operate from a supply voltage from 2.7 to 5.5 volts and temperatures from negative 40 to plus 125 degrees Celsius while consuming a very low circuit current of less than a milliamp. So how do these zero-drift op-amps actually work? Let's take a look inside. The chopper-type compensation circuit samples both the positive and negative inputs to the op-amp. The compensation circuit is in parallel with the primary amplification path. By monitoring the input, it can compensate for the input offset voltage by applying a correction through the transconductance stage GM2. This offset compensation occurs automatically behind the scenes, so you can simply connect this op-amp into your circuit and not have to worry about it. The magic happens inside the circuit. Now let's take a look at what this means in a real application. At the far left, we are sensing the current from a motor battery, so we want that sense resistor to be small, so we're not wasting power. That means the voltage across our sense resistor is going to be small, 1 millivolt in this example. So we want to use the ROHM zero-drift op-amps in the red section of this figure. They're ideally suited for use as the first stage amplifiers. They're amplifying those very small voltages, and we need to have a much smaller input offset voltage across all temperatures. So here you see that we have a 9 microvolt maximum offset voltage at that input. And we're multiplying everything by 1,000 in that red box. Our 1 millivolt signal is multiplied by 1,000, so it is now 1 volt or 1,000 millivolts. Now the input offset voltage is also multiplied by 1,000, but it is only 9 millivolts because we are using our ROHM zero-drift op-amp. A regular op-amp with input offset voltage of 190 microvolts would produce 190 millivolts at the output, an error of 19% compared to 0.9% with the zero offset type. After that first amplification stage, we can move to the signal buffering stage shown in blue. Here, we don't need zero drift, zero offset op-amps because now the signal is much larger. So you see that applying these zero drift amplifiers right up at the sensor is super critical because that's where that noise is going to get amplified along with our sensor signal. That's where we want to have the best performance from our op-amps. Comment: the breadboarding, design and test cycle by and large applies to either type of op-amps. Zero offset, zero drift op amps give designers more room to work with, i.e., predictable, constant performance over a wide range of operating and environmental conditions. This saves time, effort, and cost, reducing risk and time to market. Now let's talk about how this reduces your system design burden. This might be something you don't really think about. We're going to do a comparison of the resources required for design in two different situations. We're going to start off talking about using standard op amps. In our development cycle, we would design the circuit, assemble the product, and then we would evaluate it against the performance metrics that we need for our system, like the current sense system we just talked about on the previous slide. Tests would reveal that it would fail our standards. The large offset voltage and the temperature fluctuations due to the environmental changes cause the system to not pass the requirements that we need. So what does that mean? That means we have to go through modification. That's extra time to get product to market and extra cost for those modifications. It also may mean we need a lot of additional system resources to the design to do offset voltage correction. So not only the lost time and more design expense, but our bill of materials may have to grow as we use more components, more system resources, and additional calibration steps prior to shipment. It can require a lot more resources if we use standard op amps. Now if we look at using the ROHM Zero Drift op amps, the solution becomes much easier. Now obviously that design, assembly, and evaluation process isn't going to change. But the nice thing here is, when we get to the evaluation stage, it's going to pass. It'll meet our requirements because the offset voltages are small, and the fluctuation due to the environmental changes are also small. So we don't need to go through that extra design cycle to modify the system. It's going to work the way we want across temperature. And therefore, it facilitates design without worrying about the offset voltage. We can focus on what we need to do, sense that signal, amplify it, and pass it off to an MCU for data analysis, decision-making, and action. Before we finish today, let's talk about some application examples. We talked about this a little bit earlier in the presentation. First, let's talk about industrial equipment and consumer devices. These are ideally suited for the LMR 1002FLB. These are current sense amps for power inverters or instrumentation sense amps for temperature, pressure, and flow rate. In these types of systems, this is the amplifier to choose. And then for the automotive systems, we of course want an automotive qualified op amp, the LMR 1001YFC. For use with electronic control unit, your onboard charger, a battery management system, or any other place you're doing current sense amplification in automotive application, this is the best zero drift op amp for you to use. Whichever of these new ROHM Zero Drift op amps you employ, they're ideal for applications requiring high accuracy sensing. These are just a few examples. But you know your application requirements. If you need high accuracy with a low offset voltage and a low offset drift across temperature, these are going to be great solutions for you. They come in a compact 8-pin SOP8 package that measures only 5mm by 6.2mm by 1.71mm, so a nice compact package. In summary here, at ROHM Semiconductor, we have two new high-performance op amps with ultra-low input offset voltage and minimal input offset drift with temperature. The LMR 1002FLB is suitable for use in consumer and industrial applications. The LMR 1001YFC is automotive grade 1. Both greatly improve sensing accuracy while reducing your system design burdens, saving you effort and cost, development, as well as BOM cost. If you would like to learn more, check us out at rohm.com. Thank you for your time in listening to this webinar.